Hey there everyone, and welcome to Chemistry 3.6 on Solubility, Equilibria and Aqueous Solution. In this topic, we'll be giving a general introduction to the topic and doing a wee bit of revision from Level 2 Chemical Reactivity. So let's crack right into it. The first concept from Level 2 Chemical Reactivity that's relevant for Solubility Equilibria is the equilibrium expression. The equilibrium expression is a way of writing down a chemical reaction that is reversible. For those of you that are unfamiliar with what reversible means, it means the reaction occurs in both directions. You've got the reactants A and B, and the products C and D. However, this reaction can occur in both directions. A and B form C and D, but C and D also form A and B. You can always tell when you have an equilibrium expression because of the presence of the double-headed arrows. The second concept from Level 2 Chemical Reactivity that is important is the Kc equation. The Kc equation helps you find something called the equilibrium constant. The equilibrium constant is a number that measures how much product compared to how much reactant is present when the reaction is completely finished. To calculate Kc, you look at the concentration of all the products divided by the concentration of all the reactants. You may also remember that the number of moles is quite relevant as they become the powers that you put the concentrations to. For example, if you had 2C, then that would become the concentration of C squared. So these are quite important and don't forget them when you're doing Kc equations. If Kc is small, that means there's a lot of A and a lot of B present, but not much C and D. And so a small Kc means that there are more reactants. If Kc is large, on the other hand, it means there is a lot of products and few reactants. And so this means that the forward reaction is favoured. If we know the equilibrium concentrations of A, B, C and D, we can work out Kc. Equally, if we have Kc and 3 of the 4 concentrations, we can work out the final concentration. The most important thing to remember with equilibrium constant equations is to never include solids or water in them. The reason for this is because H2O is in such high concentration compared to all the rest of the products and reactants. Equally, solids are not included in Kc equations because they are not free to react in the same way that ions are. The final thing is remembering a wee bit about Le Chatelier's principle. Le Chatelier's principle states that equilibrium will always move in the direction that opposes change. Equilibrium systems don't like to change at all, and they'll try and keep Kc the same in all circumstances. Le Chatelier's principle can quite easily be compared to real life. In real life, if you're hungry, you eat, so you become a normal level of fullness. If you eat too much, you get too full, and you don't want to eat for a while, bringing you back to a normal level of how full you are. If you get too hot, you go do something to cool off. If you're too cold, you put on clothes or put on a heater to get warmer. This is exactly what Le Chatelier's principle is talking about, except for chemical equations. If the temperature increases, the equation will try and decrease the temperature. If one of the 4 species in the reaction A, B, C or D changes, this is going to change Kc. The chemicals will respond to this change by pushing the reaction either left to create more reactants or right to create more products until Kc is back to normal. Again, if you have any trouble with any of these concepts, give the Level 2 Chemical Reactivity work on Learncoach a look. It'll really help you going forward into the standard. So, moving on to the first concept of solubility equilibria, the saturated versus unsaturated solution. The definition of a saturated solution is that no more solid will dissolve in the given amount of solvent at a fixed temperature. This sounds a wee bit like jargon, so I'll try and explain it more simply. An unsaturated solution is a solution that is not full of a pair of ions. Let's take salt for an example. Salt, when it's put in water, turns into Na+, and it turns into Cl-. Water can only take so much Na+ and Cl- before it's all full up. When a solution is completely full of a particular solid, that's when we call it a saturated solution. And in a saturated solution, no more solute dissolves. You can try this at home if you want to, using salt and water. If you put salt into water, at first you have an unsaturated solution, and as you add salt, it will continue to dissolve into the water. Once you've added enough salt though, the solution will have become saturated, meaning the water can't take any more salt, and so the salt you put in will now just stay as a solid and collect at the bottom of the cup. Now that concept's all very nice, but what we really want to know is we want to know how much of a solid we can put in a solution before the solution will become saturated. And to work that out, we use something called Ks, and Ks is the solubility product. The solubility product is a measure of how much a certain pair of ions can dissolve into water before the solution is saturated. Ks for any given pair of ions at the same temperature is always the same number. If we take the example of salt again, NaCl, if you did 100 experiments where you put salt in water at 20 degrees Celsius, you would find that Ks for every single one of those situations was the same. If you change anything though, you change the thing you're dissolving, or you swap the water out, or you change the temperature, the solubility product will change. So the next step is how you calculate the solubility product. And luckily for us, solubility product is very strongly related to Kc. Luckily, Ks and Kc are both equilibrium constants. The only difference in them is that Ks is the equilibrium constant you use when you're doing solubility equations. The Ks equation, though, is exactly the same as the Kc equation. So let's work through an example. We have AgCl, a solid, in an equilibrium reaction, forming Ag plus and Cl minus. So the Ks equation for this is exactly the same as the Kc equation. Products over reactants. Ks equals Ag plus to the power of 1, because there's only one lot of Ag plus, and Cl minus to the power of 1 divided by AgCl. However, we have to remember the most important rule of Kc equations, and that is we always leave the concentration of solids and water out of equilibrium and solubility equations. So AgCl, being a solid, is not part of this equation, leaving us with our final Ks equation. Ks equals the concentration of Ag plus times the concentration of Cl minus. So now we understand that concept, let's do a quick couple of example questions. The first question gives us a solubility product of lead carbonate and asks us to calculate the concentration of lead and carbonate in the solution. So there's steps you always follow when doing any solubility question. The steps are: write out the equation, work out what info they're giving you and write that out, put the information in the question, and solve the question. So firstly, we write out the equation. PbCO3 as a solid is in an equilibrium reaction, forming Pb2 plus and CO3 2 minus. We then write the Ks expression, and we remember that solids are never included in the solubility product expression, giving us a Ks of Pb2 plus times CO3 2 minus. The second step is we write out the info the question gives us. So we know the Ks for PbCO3 is 7.4 times 10 to the negative 14. But how is this going to help us? Because if we put it in the equation now, we have 7.4 times 10 to the negative 14 equals the concentration of Pb2 plus times the concentration of CO3 2 minus. There are two things we don't know in this equation, which means we can't solve it. But because we've written out our equation, there is something else that we know. We know that one lot of PbCO3 turns into one lot of Pb2 plus and one lot of CO3 2 minus. Well, let's say this equation was happening in water. We now know that the amount of Pb2 plus and the amount of CO3 2 minus present will be the exact same concentration. Because when a PbCO3 splits up, it has to split into both these things. It can't just produce a Pb2 plus and not produce a CO3 2 minus. So because we know that, the concentration of Pb and the concentration of CO3 are the same number. We don't know that number, but let's just call it x for now. So if we let solubility be x, now we've got an equation that says Ks equals x squared. This is really helpful because now we only have one unknown variable and we can solve this. So you put in the Ks that you've been given, 7.4 times 10 to the negative 14 equals x squared, and consequently x equals 2.5 times 10 to the negative 7 moles per litre. Alright, then let's try another example question. This time I'll give you a wee bit of time to get ahead of me, and then I'll work through it straight afterwards. So I'll give you a minute to start thinking about this question. Now I'll walk through how I would solve it. So firstly, I'd write out the equation. I know that ZnCO3 turns into Zn2 plus and CO3 2 minus. I would then write out the Ks equation, remembering that solids and liquids are not included in the solubility product expression. This will give me a Ks equals Zn2 plus times the concentration of CO3 2 minus. Next, I would fill out what information I've been given. I've been given the concentration of Zn2 plus as 4 times 10 to the negative 7 moles per litre, and I've been given the concentration of CO3 2 minus at 4 times 10 to the negative 7 moles per litre. Using the Ks equation I've written in step 1, I can now substitute those two concentrations in and work out the Ks value. So that's what I've done there. And now step 3, solve. I've written out the concentration of Zn, written out the concentration of CO3, and I've worked out that the Ks is 1.6 times 10 to the negative 13. Now those are the main concepts for solubility questions, and being comfortable and able to do those types of questions will ensure that you get an achieved or merit on this section of the course. However, the excellence questions often involve something called the common ion effect. As we know from the Ks equation, a solution can only have a certain concentration of a pair of ions before it becomes saturated. But in all the situations we've been doing, we've been using a solution that has neither of the ions there at all to start with. The common ion effect occurs when one of the pair of ions is already present in the solution. Because there's already one of the ions you're interested in the solution, it means that you're not starting at a concentration of 0. This means less of the thing that you add to the solution can dissolve before Ks is reached and the solution becomes saturated. So I'm going to walk you through an example using AgCl in a solution of water compared to AgCl in an NaCl solution. What you can think about here is you can think of it like a basket of fruit, and this basket of fruit only contains apples. We're not interested in anything that isn't an apple. The red apples in this situation are going to be Ag+, and the green apples are going to be Cl-. Notice that Na+ doesn't have anything to do with this situation. The reason that it has nothing to do with this situation is because you're trying to add AgCl. So the only ions that might become saturated are Ag+ and Cl- ions. Na+ ions from the NaCl solution will be completely irrelevant to this question. And that's an important concept when thinking about the common ion effect. Moving back to the baskets metaphor. On the left hand side we have a solution of water. Notice how the water has no Ag and no Cl's to start with, meaning it's completely empty and the concentration of Ag+ is 0 and the concentration of Cl- is 0. This means we can add more AgCl's to the basket before the basket becomes full or the solution becomes saturated. So here I'm adding 1 AgCl to the solution and it's dissolving. I'm adding 2 AgCl's and that's dissolving in the solution too. I've added a third AgCl and it's dissolving in the solution as well. The solution is full up of AgCl's now, and so no more can dissolve. All the rest of the AgCl's that you add will stay as solids. However, in the case with NaCl, you've already got a lot of chloride present, or a lot of green apples present in your basket. This means there's not much space and the basket fills much faster. In this situation, only 1 AgCl can dissolve before the basket is full, or the solution is saturated. Now looking at these two baskets, you can see clearly which one dissolved the most AgCl. The one with water in it dissolved 3 AgCl's, whereas the one that already had chloride in it only dissolved 1 AgCl. And this can be summarized as follows. The common ion effect is when the ionic solid dissolving and the solution share a common ion, and the solubility will be reduced. Another important point about the common ion effect is you measure solubility by the not shared ion. And you might be wondering what I mean by that? Well, if you calculated the solubility of AgCl by counting the concentration of Cl's, you're going to say lots of AgCl dissolved. But that's not true. Lots of NaCl dissolved, and a tiny bit of AgCl dissolved. So to calculate the concentration of AgCl that's dissolved, you have to measure the ion that's not shared, the Ag. And the concentration of the Ag will tell you the solubility of AgCl. So hopefully I didn't lose you there, but let's work through another example to solidify our knowledge. So what we're doing is we're calculating the solubility of barium sulfate in water versus the solubility of barium sulfate in a 0.1 mole per litre sodium sulfate solution. The Ks of BaSO4 is 1 times 10 to the negative 10. So let's start by doing it in water. Same 3 steps apply that always do. You write out the equation, and you work out that's a 1-to-1 ratio. You write out the Ks equation, remembering not to include solids in it, and then, because it's a 1-to-1 ratio of Ba2 plus to SO42 minus, we can call Ba2 plus x, SO42 minus x, and have an equation Ks equals x squared. We then put in the information we're given, Ks equals 1 times 10 to the negative 10, and we solve. So hopefully that was nice and easy. So now we're going to do the same thing, except instead of being in water, the BaSO4 is in a 0.1 mole per litre sodium sulfate solution. Now the first thing you need to do in questions where the common ion effect is asked about is to identify which is the common ion. So to do that, you write out the equations. I suggest when you do this, you keep the equations separate so you don't get confused about where you're putting your numbers. So on the right, we have our equation BaSO4 going to Ba2 plus and SO4 2 minus. And then we've written out the Ks equation and worked out there's a 1-to-1 ratio of ions. This is exactly the same first step we did for BaSO4 in water. The extra step is we're going to write out the equation for sodium sulfate. So sodium sulfate as a solid turns into 2 Na plus and SO4 2 minus, a ratio of 2-to-1 ions. The reason we've written it out is so we can identify what the common ion is. And so as we can see quite clearly now, the common ion is SO4 2 minus. The next step is putting in the information we know. So what info does the question give us? One piece of info the question gives us, the concentration of Na2SO4 is 0.1 moles per litre. We also know Na2SO4 is in a non-reversible reaction to 2 Na plus and 1 SO4 2 minus. Using these two pieces of information, we can work out the concentration of SO4 that's present before we add any barium sulfate. In non-reversible reactions, all the reactant is used up. All the Na2SO4 has split into Na plus and SO4 2 minus. Every Na2SO4 that splits gives off 2 Nas and 1 SO4 minus. So from this we can work out that for each litre of Na2SO4 that splits, it will create 0.2 moles of Na plus and 0.1 moles of SO4 2 minus. So now we know how much SO4 2 minus we've started with before we start calculating the solubility. And so the third step is to solve the question now. We know that Ks equals Ba2 plus times the concentration of SO4 2 minus. We know that Ba and SO4 split in a 1-to-1 ratio in barium sulfate. So you can call Ba X and you can call SO4 2 minus X. However, you have to include the amount of common ion present before you even added any BaSO4. And as we know, because we worked it out in the previous step, there is 0.1 moles of SO4 2 minus present. So the equation becomes X times X plus 0.1. For those of you sharp on maths, you'll be able to see already that this is going to form a reasonably nasty equation. Ks equals x squared plus 0.1x. There'll be multiple x's in the equation and it'll be difficult to solve. However, we can take a wee bit of a shortcut here, and the reason we can do that is because the Ks value for BaSO4 is very, very small. Why is that relevant? Because if you remember back to the very first slide, small Ks values mean that almost all BaSO4 stays as reactant. So almost all of the BaSO4 stays as BaSO4. Only a very small amount turns into Ba2 plus and SO4 2 minus. The amount of BaSO4 that splits is in fact so small that it will be nowhere near 0.1. So in this expression, you can ignore the x. Think of it like adding a very small number to a very large number. If you have $1 million and someone gives you $1, you still have approximately $1 million. You technically have 1,000,001, but does that make a difference when the 1 million is so big? So though it won't give us the exact right answer, it will give us a close enough one. So what we do, instead of going x plus 0.1, we can just say 0.1. This makes the equation significantly easier, because now Ks equals x times 0.1, which equals 1 times 10 to the negative 10, x equals 1 times 10 to the negative 9. Tying this all together now, let's have a comparison of the solubility of BaSO4 in water compared to in sodium sulfate solution. And you'll see it's quite significant. The amount that could dissolve in water was 1 times 10 to the negative 5 moles per litre. The amount that can dissolve sodium sulfate solution is 1 times 10 to the negative 9 moles per litre, which is 10,000 times smaller. And this proves that we are right in saying, due to the common ion effect, the solubility of BaSO4 has been reduced. So now I'm going to give a quick summary of what you need to know from this introductory PowerPoint. You need to remember that Kc is the equilibrium constant, and you need to have a general idea of what that means. You need to understand what a saturated solution is, and you need to understand what an unsaturated solution is. You need to know that Ks is a solubility product and have a general idea of what Ks means. More importantly though, you need to be able to write out equilibrium expressions, and you need to be able to do Ks values for equilibrium expressions correctly. You need to remember never to include solids and never to include water in Kc and Ks equations. Finally, a little bit of extra for experts. You need to understand what the common ion effect is, why it does what it does, and you need to be able to calculate the difference between a solid being put in water and a solid being put in a solution that has a common ion. Thanks for tuning into this introductory PowerPoint. In the next session, we're going to be looking at solubility a wee bit further, and then starting to move on to some acid-base chemistry.